So, you've made it to the last section of the course, the project. Well done, and congratulations on making it this far. Hopefully, you've found out some interesting things about high-speed flows and about scramjets. Now it's time to put what you've learnt into practice. In the project, you'll analyse the performance of a simple scramjet engine. The configuration is the one that we've been using throughout the course. It's a two-dimensional scramjet engine. It has the 3-shock inlet, a constant area combustor, and an isentropic nozzle at its exit. The fuel will be hydrogen. The ultimate goal of the project is for you to determine the specific impulse for an engine configuration and flight condition that we'll give you. Each student in the class will be given their own configuration and flight condition, and we will collate the results to produce a plot showing how the specific impulse varies with flight Mach number for this series of engines. In analysing this engine, you will make some simplifying assumptions. The first is that the engine is two-dimensional. This means that the width of the engine, the dimension out of the screen here, remains constant along the entire length of the engine. Therefore, there are no variations in properties of the flow in that dimension that comes out of the screen. And to make it simple, your engine will be 1 metre in width. Next, you'll assume that the air passes through the engine is a calorically perfect gas. This means that the specific heats remain constant. This assumption will apply throughout the inlet, the combustor, and the thrust nozzle. You now know, from what you have done so far in the course, that this is just an approximation, particularly when the gas gets hot in the combustor. The gas passing through the combustor is actually a combination of the air and the combustion products, but we'll assume that it's just the air. Related to this is another simplifying assumption that you'll make. You'll assume that the mass flow rate of air passing through the inlet is large compared with the mass flow rate of hydrogen being added into the combustor. Let's just zoom in on the combustor. If we say that the mass flow rate of air passing through the inlet is m dot, and that the mass flow rate of fuel being injected into the combustor is m dot f, then, by conservation of mass, the mass flow rate leaving the combustor must be m dot plus m dot f. Our assumption that the mass flow rate of fuel is small compared with the mass flow rate of air allows us to say that m dot plus m dot f is approximately equal to m dot. And our assumption that the air is calorically perfect means that we don't have to include how the fuel and its combustion products change the properties of the air. So the only effect of combustion will be an increase in the temperature of the air passing through the combustor. We'll also neglect any viscous effects in our engine. This is another major simplifying assumption because we know that viscous drag can be significant in high-speed flows. But we've only been able to include a brief introduction to viscous drag effects in fully developed duct flows in the subsection on Fano flow. We'll therefore ignore any viscous effects on drag on the inlet, in the combustor, and in the thrust nozzle. This will make the analysis more tractable and will give us a higher performing engine than if we were able to include viscous drag. The final simplifying assumption that we'll make is that we'll only consider the internal flow path for this engine. This is shown here as the hatched area. That means that we will not be considering the drag forces on the external surfaces of the vehicle. In the next video, I'll cover how you'll be given your particular flight conditions and geometry.